Okay, I think we can start. Good morning. Welcome at the second session this week. And as you can see, we will still cover stuff from chapter 11. We will still talk about the convergence and divergence of the series. Okay, can you hear me? Because I don't want to talk. Yes, okay. I think the audio is good. Okay. Because I was playing with this external voice and the internal microphone, and I don't know, I hope I didn't mess up stuff. Okay, that means just before I start, just a quick reminder, we still have few, you can't hear me, but if the other students can hear me, maybe it's on your side. Because if you will not hear me at all, then it's on my side, but you can maybe, okay, yes, yeah, you can, that's the good idea. You can maybe try to leave the classroom and come back. Okay, that's me. Just a quick reminder. We do have two weeks, like a little bit more than 2 weeks before the second midterm, and I just want you to make sure that you booking your appointment on Examity. Most of you did a really good job last time, but we had few problems. That means let's just avoid this and let's go to the Examity site and book your time. We do have the few days to take the midterm too, and I think it's open from July 5th to July 9th, from Thursday to Monday, as always. Yes, thank you for muting the microphone, whoever that was. Okay, that means just please make sure, do not wait until the last day, and especially Monday. You can't take tests like Monday 10 a.m. I mean 10 p.m. because you need 90 minutes, and of course you can't, at midnight everything will be locked. And the same actually applies for the final. You can find on the calendar the time window for the final test, and you can also try to book your time. Then you will be comfortable, you will have your day, and you will manage your calendar better. Okay, that's me. Let's start. What I will do, I will carry on with the test for divergence and convergence. That's what was introduced yesterday by Dr. Bang. That's mean what we did. Last week, I did introduce the sequences. But yesterday, you learned about the infinite series, which means if we take the terms of the sequence and instead of like just listing them, put like a sub 1, comma, a sub 2, comma, what we can do instead of commas, we can add the term a sub 1 plus a sub 2 plus a sub 3 and so on. Then we creating infinite series. Okay? That means the sum of the terms of the sequence are giving us series. And what we have to do, we have to find out if the sum is convergence or the sum converges or diverges. Okay? That's we know what this means, and we do have lots of tests. Some of them are quite easy. Some of them are a little bit more like challenge, I would say. But they are good tools. And yesterday, I think you learned, what did you learn? Yesterday, I believe you learned about the geometric series, okay, that we know how to recognize and how to determine whether the geometric series is convergent or divergent, and also the telescopic. Okay? That's nice, 2 types. And for these 2 types, actually are also good thing, because when we recognize the type and when we do the whole process, we can find actually the sum if the series is convergent. If it's divergent, of course, it's divergent, big number or undefined. But if it's convergent, we can find actually the sum. Probably you can probably still learning this, and you can think how it's even possible to add infinitely many terms and have a finite number. But of course, if the terms are getting smaller and smaller, and if the terms are getting smaller and smaller fast enough, then we will be adding and adding and adding the terms, but we will never expand the whole sum. The sum will be like not greater than 1 or 2, like a finite number. Right? I know it's quite weird property, but that's how it is. Okay, that means not always, you can see my notes, not always is easy to find the partial sum. We know what partial sum is. Like if I add 10 terms, I have S sub 10. I add 10 terms. If I add 1,000 terms, that's my S sub 1,000. That will be the partial sum. That means it's not always easy to find the sum, right? Which means to compute the behavior at infinity of the partial sum. That means what we will do today, I will show you a few tests, okay, that based on the test, we can only determine whether the series is convergent or divergent. We will not really find the actual sum if it's convergent. Okay? Maybe later we can just add something, but for now, we have to know some tests, and it's enough. And it's enough to say, okay, this series is convergent, this series is divergent. And that's it. Okay, we will try to estimate. Okay, that's what we have. Before actually I start introducing, because the test for today is the integral test, and the second test is the comparison test. Okay? Integral and comparison. Okay, but before I start, I copy one slide from my from the last week from sequences. Let me just, because we have to determine whether the sequence, just the sequence, which means all of the terms, whatever, if we're adding or not adding, if we're adding, we have series, if the sequence is increasing or decreasing. That's really important, okay? Let me go through this. I will switch off my video because it's covering the slide and it's not really, and it's also slowing down. Okay, that means we know that A sub n, the sequence, it's something like function. Yeah? We do have a formula. We can check how this behaves at infinity. We can like do everything. That means we also have to find out if the terms of the sequence behaving like that, which means if they are getting bigger and bigger, increasing, or maybe they are getting smaller and smaller, decreasing. Okay? That means this is the definition of increasing sequence, which means next term, we know what A sub n plus 1 means. Next term will be always greater than the previous one. And like, let's say for the increasing, what I can give you, I can give you an example. Maybe just n. Okay, that means the first term is n. The next one will be n plus 1, n plus 2, n plus 3, or if we like, I can just list the numbers like 1, 2, 3, yeah, just the numbers. Of course, it's definitely increasing. Okay? That means we can definitely say that A sub n is always less than the next term. Okay, for the decreasing is the other way. Okay, if the next term is smaller, always for all n, then the term is decreasing. And I can give you an example. Let's take the easiest one, 1 over n. Okay, 1 over n has the terms like 1, and then 1/2, 1/3, 1/4, and so on. That means I can definitely say that always the next term, which this is one term, this is the next one, it's always smaller. Okay? That means 1/3 is less than 1/2, 1/4 is less than 1/3, okay? And so on. That means this works for all n, the natural numbers, counting numbers. for all n values. Okay? But what's happened? Sometimes if we will ask you to prove that the sequence is decreasing, you can probably just state this. You can say, yes, it's decreasing. But also, sometimes we need a little bit stronger proof. And hopefully we remember, do you remember like the calculus-wise? Because this is just algebra. How can we prove, how can we find an interval of decrease or increase, of course, having the formula of the function? That means, do you remember from calculus 1, if you had the question, please find the intervals of decrease for the given function. And I can even write, and let's even say 1 over x. That means, how would you, what we will do with the function 1 over x to find an intervals of increase or decrease? Derivative, yes, and the critical numbers, yes, thank you. That's my point. That means actually proving, yes, I mean going through the calculus, finding the derivative is the easiest way. The easiest way sounds a little bit time consuming, but it's actually not. That means, let's see. I will find the derivative of 1 over x, which is negative 1 over x squared, and we can see if x is positive, because of course having x, I can accept any numbers except 0. But having n, I'm always thinking about the positive numbers. That means if x is positive, but in this case doesn't even matter because I'm squaring. Okay? That means x could be any number. But just for positive, because that's what we're looking for, positive values, this expression is negative 1 over x squared, which means the derivative is always less than 0. Actually, I can even say for all x's from the domain. Okay, that we can see derivative is always less than 0. If derivative is always less than 0, then the conclusion is function is always decreasing. Decreasing. Okay, we can see that. This is a really good proof. If you end up having the question like that, you have to make sure that your function, your sequence is decreasing, find the derivative and show, and especially decreasing. Okay, especially decreasing. Because we will learn today, and what was the test yesterday? No, but yeah, you will see. We have to really prove that the formula is decreasing. Because if it's increasing, it doesn't make sense. The terms are getting bigger and bigger. We will add them together. Of course, we will always have huge sum divergence. But if the terms are getting smaller and smaller, we still have to investigate something, but at least it's decreasing. At least is the condition checked. That means, please remember, use the derivative, like I did for this one, because it's really showing me that it's negative. That's what I need. Okay, that means now let's start. Integral test. As I said, geometric telescoping. Okay. That means we will start investigating this series, the summation from 1 to infinity of 1 over n squared. Okay? That means what we have 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, and so on. Okay? That means actually what you can say about 1 over n squared, just thinking about the sequence, because that's the sequence, a sub n. Is this sequence decreasing? Yeah, other terms are getting small. It is decreasing, yes, okay. But again, I have to really, probably I will repeat this maybe every 5 minutes. If it's decreasing, it still doesn't, it's not really a test. I still can't really say, oh, it's decreasing, that means it's convergent. No. We always have to check if it's decreasing. Almost always, but we still need other things. But yeah, it's definitely decreasing. That means the sequence, I can just pull out the sequence, is decreasing. Decreasing. For all of course, for all n. Because it's getting smaller and smaller. Okay, that means at least we identify this. If I will try to think about if I would like to compute a derivative, Also derivative will be negative for positive values. That means it's definitely decreasing, but we can see. If it's so obvious, we can just simply state it's decreasing. Okay, that means what we will do. Of course, this is not in terms of the partial sum. Yeah, it's not a simple formula like to add together. I don't know if Dr. Bank was showing you a few things. I think he did compute the partial sums. But as I said on my first slide, it will be not easy to look at the partial sums, which means like, what is the number to add the first two terms? What is the number to add the first three terms? What is the number like, and then looking at these numbers, we will like find out how this behaves at infinity. That means no, it's not really an easy process. That means what we will do something like that. First of all, I can show you a numerical values, okay, which is not always the perfect proof, but at least something. That means I just change for n, I mean, I did replace infinity with n, and I just introduce new, like, yes, letter 1 over I squared is the same thing. I is changing from 1 to n. And of course, n could be infinity. And now let's see. That means this, what it is, this is the partial sums. Okay, I can show you. Okay, I can show you this. That means if I will find out, I mean, if I will add together 5 terms, okay, I will get the number 1.4636. You can even use the calculator and you can check. Now, that's what I'm saying. 1, 2, 3, 4, 5. If you will add this, you will get 1.446. Okay? And then if you will add like more terms, 10 terms, you will get the number 1.5498. 50 terms, 1.62. Let's say 1,000 terms, 1.6439. 5,000 terms, 1.6447. That's when we can probably notice, and I can keep expanding this partial sum, but I can tell you, doesn't really matter how big is n, I can have infinity many terms adding together, and the sum will be not greater than 1.64. Okay, that means it's funny, right? Because we adding and adding and adding, and the sum will be not greater. We will always will be greater, but never greater than 1.64. Which of course, the sequence, I mean the series is convergent to that number, okay? And let's look at the proof a little bit more like geometrical, not a geometric series, no, just the graphical explanation. That means what I did, I took corresponding function 1 over x squared. We know the function 1 over x squared is the hyperbola in the first and the second quadrant, but since we only looking at the positive values, 1, 2, 3, 4, we have this pink curve. And I will draw a rectangles like I did. Yes, we can see the rectangles starting from 1, 1, 2, 3, 4, and so on. That means the base of each rectangle, it's 1, because by 1. And then the height is just the value of the function at the endpoints. That means the value is, the height of the first one is the value of the function at 1, which I have to substitute 1. The height of the second one is the value of the function for the second one, for the point 2, which will be 1 over 2 squared, 1 over 3 squared, and so on. And the base is 1, that means base times height, that's the areas. Okay. And if I will add all of these rectangles, yeah, look at this. 1, I mean, the area of all of these rectangles actually are giving me my sum, my series, okay? But now what I will do, I will try to compare this because I still don't know. I know that it's 1.64, but I still want a little bit like stronger proof. That means what I will do, I will, okay, I do have this on my, okay, I can write for you. That means what I will do, I will ignore the first one for now because it's just 1. You hopefully remember the definite, improper integral from 1 to infinity of the function 1 over x squared dx, which is starting from this and is the entire area under the curve, and of course, the limit is infinity. Do you possibly remember from section 7.8, do you remember that value? We can probably compute really fast, but hopefully somebody remember, because that was definitely convergent. Yes, we did use the same terminology. I think that integral was 1. Okay, yeah, makes sense? You can definitely check, because I don't wanna spend time. You can definitely integrate this, you can look at the limit. Okay, this is 1. And now, if this integral from 1 to infinity, I think we can try to compare. And of course, this is 1. That means having this, and I have here, I have extra things. That means this is theoretically my integral. Okay, but let's, I mean, if I would like, yes, to compare, but because I didn't include this one. But let's see what's happened. The integral is 1. But can you see that the integral actually covers more area than the rectangles? Can you see like this? Because we have more space below the curve if we're looking at the entire area below the curve and comparing to just the rectangles. That means this rectangles covers less than this one. That means integral is definitely greater. Okay, we can see integral is definitely greater than, I can even move that one maybe on the other side because we don't have to really. But what is my point? If I have something that is convergent, which means the sum exists, the number exists as a finite number, and something what is smaller, it's also must be convergent, because smaller means kind of like it's inside this. Like we can think that this is like a big box and it's convergent. It's like we have the finite volume. Everything what is smaller is convergent too. And that was the comparison for the improper integrals. That means what we will do, we can conclude. Yeah, I'm just adding this extra. We comparing, okay? That means yeah, I have the other way. My sum is smaller than something finite, something convergent. That means I can say that this is convergent too. That means this is definitely a proof that the adding infinity many of these rectangles will be always even less than 1, or adding this extra less than 2. Okay? That means this is proof that is convergent. And because we're using some, I don't really want, it's just decreasing. But what is the important thing? In order actually to use this property, function must be positive, okay? And function is positive. Oh, but I wanted, hang on. Let me just, this should be actually decreasing. Hold on, no. The whole terms, they have to, because we have to, as the terms are positive, I'm just, the partial sum converges, but this must be decreasing. No increasing. I mean, n is getting bigger, but the whole terms, okay, the whole terms, I mean, all of the terms of the sequence, they have to be decreasing and positive. Okay? And then we're using this monotonic sequence theorem, and then we can conclude convergence, which actually is just this, we comparing. Okay? Okay, but now let's look at the next stuff, because I will still have a summary of this, what I said. It's decreasing, positive, and continuity, but I will add this later. Okay, just the conclusion. This sum is, as I said, is less than 2. We proved that. You can also check this number, because this series is quite famous. And one of the mathematicians, Leonhard Euler is the German name, he actually also played with this, and he even discovered that this number, we just learned that is 1.64, but he even find out some like a number like that, pi squared over 6. That means when we will be adding and adding infinity many terms, the terms are less than 2, which of course is 1.64. We knew this from the numerical proof, and he even defined this like that. But of course, it's just for fun, this information. Okay, now let's look at this one. This one is a little bit different. We do have a series similar to the previous one, 1 over square root of n. And I can only tell you that the function, if I will draw a function, looks really similar like a hyperbola. Like hyperbola, a little bit higher because the values are smaller in the denominator. Okay, but I will draw this later. And now we have to actually look at this and think if this sum is convergent or divergent. And what do you think? Is this convergent or divergent? Like 1 over 1 plus 1 over root 2 plus 1 over root 3, 1 over root 4, and so on. Yeah, of course, it's okay, it's divergent. Oh, I think it's the right answer, but let's prove it. That means, first of all, let's see. Okay, I can write here the sequence. If I pull out just the sequence, do you think this sequence is? We actually see the terms of the sequence. It's decreasing or increasing? Are the terms getting smaller and smaller? Yes. Oh, no. Increasing? Oh, yeah, no. The first term is 1. The next one is this. The other one is this. The next one. Oh, and so on. That's what do you think? It's decreasing. Please remember, if denominator is getting bigger and bigger, the whole fraction is getting smaller and smaller. Okay, that means definitely this is decreasing sequence. Decreasing. Okay? That's what, yeah. Okay, that means it's similar situation to the previous one. The terms are getting smaller and smaller and smaller. But the question is, are they getting smaller fast enough to actually get the sum as a finite number? Right? That means I have the numerical values like I did for 1 over n squared. And let's look at this. Let's look at these numbers. If I add 5 terms, 3.23. If I add 50 terms, 12.75. If I add the partial sum like of 1,000 terms, 61. 5,000 terms, 139. That we can see as n goes to the infinity, this number is also huge. Okay, that means it's definitely, it's not really approaching a one finite number. The sum actually accumulates huge number. That means the series is divergent. That's when we can see we have to be really careful. Even if the terms are getting smaller and smaller, right? We can still have like different type of the series. One more thing, because I want to add, if I will ask you to compute a limit of this sequence, because you remember that was the big thing in section 11.1. What is the limit at infinity of this sequence, of this expression or function? It's 0, because 1 over infinity, of course, is 0. And I will just write down, not x, what is the limit of the previous one, n squared. That's what I prove. What is the limit at infinity of this? Oh, it's also 0. Thank you. Thank you for answering my question. That's when we can see limit at infinity is 0, of course, because it's decreasing. I mean, not always when the limit is 0 is decreasing, but most likely. And this one also has 0. And we can see this, not sequence, the series was convergent. This series is divergent. And that means this is also, please do not get confused. 0 means I can say now, it's helpful to know, because at least we do have a chance for convergence. But 0 is telling me nothing. Okay? You remember this from 11.2. It's actually almost a test for divergence. Okay? That means if the limit of the sequence is 0, we know nothing about convergence or divergence, but at least we do have a possibility that could be convergent, but also could be divergent. Okay, that means let's look at this. That means the terms are getting smaller and smaller, but probably not fast enough. That's the main thing. That's what I will do. I will do the same thing. I will draw a function 1 over root x. I will start from 1 and draw the left-hand side rectangles. Okay? Each base is 1. The height is the value of the function. That's the area, which of course, adding the areas, I have my series. And now it's the same thing. If you remember from section 7.8, improper integrals, 1 over root x, this integral was divergent. And do you remember? Because x is taken to the power of 1/2, and 1/2 is less than 1. Okay, that was also I mean, that we had the main conclusion. Okay, that's me now. If I will compare this from 1 to infinity, integral from 1 to infinity, 1 over root x dx, and I know that this is divergent, which means like huge number, infinity. And my rectangles, which is my series, they actually sticking out. Can you see? That means they are definitely greater. And again, perfect. If this is like infinity, I can say everything what is greater is also infinity. That means this is a perfect proof that the series 1 over root n is divergent. Okay, that means that's enough of all of the proofs. Let's make the conclusion and let's define the test. I can also make a small comment. You don't have to like prove it. That's what I did. You have to just use that tool test. Okay, that's what I did on the other side. This is divergent. Everything what is greater, it's also divergent. Oh yeah, we remember that. Okay, that means the area is infinity. The sum must be also infinity because it's bigger. Everything is divergent. Okay, that means this is, since we use everything like I did compare with the integral, we will call integral test. Okay. That's what we will do. You have to just use that page. Having a sequence, I mean having a series, starting from 1, ending at infinity. Okay. That means having a series, of course, we're just taking a sequence and we're testing this formula, a sub n. And what we have to know, I mean, what we have to check, this formula, this function or expression, this sequence must be continuous. Okay, we can see, yes, for all of the numbers from 1 to infinity. All of the terms, they have to be positive. Please remember, we can't have like alternating, like -1, +1 now. All of the terms, they have to be positive, like above the x-axis. And of course, decreasing. The terms, they have to be decreasing. If they are not decreasing, that's not, I mean, that's not a condition for the integral test. That means when you check all of this hypothesis, all of this condition, then we can conclude this. If the corresponding integral is convergent, then always conclude the convergence of the series. If the corresponding integral is divergent, then the infinite series is also divergent. And you don't have to really prove everything always works, like I show you with these rectangles. Okay? And when can we use the integral test? Especially when we look at the formula and you will like think, oh, I know how to integrate. Because when you know how to integrate, you can take care of the integral. Taking care of the integral, you will determine whether it's convergent or divergent, and then you have the answer, basically. Okay, let's solve one example. Okay, that means let's come back. I have one, yes, I have comments. I said that function must be like, I mean the formula, continuous, positive, and decreasing starting from 1. But we can also have the situation that I can skip, like as always, I can skip a few finite numbers. Yes, we can see, it depends on the formula. I can say that I am function, I mean the formula is satisfying all of the condition, but starting from n equals to 4. It's still fine. Yeah, it's still fine. We kind of call like ultimately decreasing, or ultimately like we satisfying this condition starting from different number. Missing a few finite numbers doesn't change anything in terms of convergence or divergence. This is important, right? The behavior at infinity. That means I can skip few numbers at front. Okay. Oh yeah, that's the same thing. If the function is not decreasing starting from 1, or it's just decreasing starting from different number, it's still fine. Okay, I'm just looking at my example, but I have lots of notes. Okay, that we can see we're using the integral test, but please remember, it's only a tool, it's only a comparison. That means even if I will say that the improper integral, which I am comparing, it's equal to 1, and I'm comparing with my infinite series, overall, in general, the integral is never the same like the infinite series. Okay, please remember, because that box is really nice question for the true and false. Yeah, like using the integral test, we comparing an integral with the infinite series, but we only comparing. You remember, we will always have the situation that my summation, the rectangles were always bigger or smaller. Never the same. That means even if I'm comparing that, oh, this is convergent, then this is also convergent. It's fine, but they are never the same. Please remember, if I will type the equal sign, you have to say on the test that is false. Okay, let's do this one. Test the series of the summation, the series of 1 over a quantity n squared plus 1 for convergence or divergence. That means we can see it's nice, yes, it's nice formula, and it's definitely really nice for the integration because we know how to integrate 1 over x squared plus 1. Okay, that means since we're talking about the integral test, I will use the integral test. Integral, okay, I didn't type, I have the solution, but I will write for you, integral test. Okay, I will maybe copy this as a function. That means I'm looking at this formula, and I can definitely see that my function is continuous function on the interval from 1 to infinity. It's definitely positive. Positive. On 1 to infinity. And now, do you think it's decreasing? Decreasing, because I always have to check this. This is definitely, I will put the question mark. What I will do, I will find the derivative really fast. I can rewrite this function as a x squared plus 1 to the negative 1, just for the derivative purpose. And derivative will be negative 1, quantity x squared plus 1 to the negative 2 times 2x in a function. And I will rewrite this, negative 2x on the top, x squared plus 1 squared. Okay, that means if x is positive, because x is theoretically n is always positive. If x is positive, I will always have this expression less than 0. That means this is for all x great, let's say positive, real positive. Okay, that means that's the case that I can say function is definitely decreasing. Okay, Now I think I can use the integral test. That means I can integrate my function from 1 to infinity, 1 over x squared plus 1 dx. It's improper integral. We do have to replace infinity with t, and t goes to infinity. X squared plus 1. Okay, limit t goes to infinity. Can you tell me the antiderivative or integral of that? 1 over x squared plus 1? Oh, do you remember? What's the integral of this? I hope I have students in the classroom. Inverse tangent, thank you very much. That means this will be inverse tangent of x from 1 to t. Okay, limit t goes to the infinity, tan inverse at t minus tan inverse at 1. Tangent for what angle is 1? I know, I want you to answer. Tangent for what angle is 1? Yeah, it's the inverse, that means I have to ask this way. Tangent of pi over 4 is 1, excellent. And how inverse tangent behaves at infinity, because t is infinity. How inverse tangent behaves at infinity? Pi over 2, thank you. Oh, we can see I don't even have to subtract them. I will, but theoretically I'm not even looking what number is this. As soon as it's the finite number, the integral is convergent. If the integral converges, the infinite series is convergent. Convergent, and we can say by integral test, IT. Okay, that we can see. It's a little bit time consuming because you have to check these conditions, probably the derivative, and then you have to integrate. Okay, but it's nice, good, solid tool. Okay, that's the way to solve it. I do have the other examples, but maybe I can leave it for you because that's what you have to do. You have to solve the corresponding integral, check if you're getting finite number or infinity, and then make the conclusion. And of course, testing this hypothesis. And I will just double check. Pi over 4 doesn't mean anything. It's not the sum. No, we can't say. It's just telling me that it's finite number and it's convergent. Okay, I do have this. Okay, I have another one. What do you think? Shall I solve one more or shall I jump to the next test? Determine whether this series ln of n over n is convergent. It's up to you. Okay, I can leave it for you. If you want me to solve it, we can go through, because I think we can also integrate easily. Do you know how to integrate? Let me just ask you. Do you know, because we have to, oh, okay, this one is actually, just one thing is, okay, one thing is different. I was gonna write ln of x dx. It's infinity, but this number will be a little bit different, but doesn't change anything. Like, but please answer my question. Do you know how to integrate this function? Ln of x over x, what techniques to apply? Technique is the u substitution. Yes, of course. Okay, actually, you know, let's maybe try integral test. Because it's one, I just realized it's one thing. Ln of x over x. That means if x is positive, the whole function is definite. I mean, first of all, continuous. That means it's definitely continuous function. Okay, we will change something here. It's definitely positive, ln of x. But now let's look at this, decreasing. Decreasing. Okay. Let me find the derivative because that's the easiest way. I have to use the quotient rule. derivative of ln of x is 1 over x times denominator minus ln of x times what? X squared. So the derivative looks like 1 minus ln of x over x squared. That means what I want this expression to be negative. X squared is always positive, no problem with this. That means I have to focus on numerator. 1 minus ln of x must be less than 0. Let's solve it. Subtract 1, multiply by negative 1, changing the direction, and ln of x, ln of e is 1, and then I can drop the logarithm. I can only focus on the inputs. That means x must be greater than e, then this expression is negative. Okay, that's you can see that's what I just realized that I can tell you, when we have natural logarithmic, everything works. We will satisfy all of the conditions, but not starting actually from 1, starting from e. But since e is not really an integer, we will just integrate, and we will pick, because n is the n is the integer, right? That means I can't just put 2.7 or e. I will put 3. 3 because we're thinking, and normally I can even say 3. Doesn't matter if I skip a few terms, doesn't matter. But starting from e, this function is decreasing. Okay, decreasing on the interval from e to infinity. But since I can't use e, I will put 3. Okay, and then we can integrate, because now we definitely satisfying this, we allowed to use that integral. Shall we integrate this? I will integrate from 3 to t. T is infinity, and one more time, ln of x dx. Using the u substitution, I will let u to be ln of x. Du is in my denominator. 1 over x dx. Let's try. Limit as t goes to infinity. 3 over t. Actually, let me skip the limits for now. It is just u du. Because having a limits of integration and new substitution, I have to have new limits. That means ln of x, this will be ln of 3, ln of t. Okay, and integral of u du is just u squared over 2. ln of 3, ln of t. But we can see as soon as I substitute ln of t is infinity. Infinity squared is just infinity. That means this will be big number, divergent. Because that's infinity, that's finite number, but doesn't matter. This will give me infinity. Okay? That means this is diverges by integral test. Okay, yeah, that's a good thing because that e value. Okay, let's see what I have next. Yes, divergent. Okay, that means we may also have a really simple infinite series, which we will have, which it will have that form, like 1 over n to the power of p. And p could be theoretically any number, okay? Any number. And as we found, okay, in section 7.8, for the improper integrals, that if the integral from 1 to infinity, 1 over x to the power of p, and if the p value is greater than 1, which means the terms are getting smaller and smaller fast enough, we will have convergence. If the p is less than 1 or even equal to 1, the terms are getting smaller but not fast enough. We will accumulate huge number, divergent. Okay? That means since we're using the integral test, we can compare integral with the series, and the same properties we will hold for the infinite series. And sometimes we will call a p-series test, but some of the mathematicians, they still like to name this integral test because it's based on the integral test. But I think we will call p-series test because it's just based on the p value. Okay? But we have to, just in case, we have to know that the integral test is behind this property. Okay? That means please remember, if the p is greater than 1, convergent. If the p is less than 1 or equal to 1, divergent. And I have these two. Okay, determine whether the series is convergent, series converges or diverges. What about this one? Can you tell me? Convergent or divergent? No? It's convergent because I can say p is 3, greater than 1, converges by p-series test. Or you can say by integral test. Okay, I mean, the same thing. Okay, what about exercise number 5? Does this series, of course, is divergent. I know, it's funny, so easy and simple, but you will see how often we will use this. That will make sure, yes, make sure that you know the values. And it's actually the same conclusion. Oh, but it's divergent. Wow, wow. Divergent. Okay, I can say by integral test, but it's also the p-value. Okay, and this one. Actually, I have one more exercise, but what do you think? What do you think about this series? N plus 2 over N plus 1. It's divergent, yes, diverges. But can you tell me, Pete, can you tell me why it's divergent? It's divergent. What test we can apply? Oh, yeah, it's actually nice to see almost right away. Because it is not equal to, I don't know, I think I know what you mean. You're saying that the limit of the sequence, yes, the limit of the sequence is not 0, right? That means, do you remember yesterday the test for divergence? Probably next week I will give you, or maybe even is now on Canvas, because what you have to know, you have to have a big list of all of the tests. Okay, like I introduced today the integral test. I will still introduce the comparison test. And you had the geometric series, you have the telescoping one. But the first test that you learned probably yesterday was test, we will call test for divergence. That's what this means. You have to take this formula and check the limit. Okay? How this sequence behaves at infinity. Okay, and what is this limit? Yes, the limit is, it's 1, thank you, it's 1. That means what this means, if I have a sequence, that means it's not 0. That means if it's not 0, we have no chance for convergence. That means this infinite series is divergent by test for divergence. Okay, and what this means, because sometimes we can get really confused, you will see, oh, it's 1, it's a finite number, that means it's convergent. No. 1 means that these terms at infinity becomes almost 1. That means if I would like to make a list of these terms, oh, what will be? This will be 3 over 2, and then 4 over 3, and then 5 over 4, and eventually 1. Right? That we can see they're getting Are they getting bigger and bigger? Because yes, they're getting bigger and bigger. No, 3/2. Are they getting, because they are not increasing. Yeah, they get, oh no, they're getting actually smaller. Oh my gosh, smaller. Because 3/2, this is less. This is 3/2. It's bigger. That means they are actually getting smaller. I'm just trying to explain. That means 3/2, 4/3, 5. Yes, they're getting smaller, but they will never get smaller than 1. Like 6/5 and so on. That means they will really have 1. That means what this means, at some point they will be almost 1, almost 1, almost 1. If I add a series, this means that I am adding these terms. Even if they decreasing, we can see they not. That means I will be adding, and eventually I will be adding 1 plus 1 plus 1 plus 1 and plus 1. That means this means that I will be adding all of these ones. Of course, I will create like a huge number. Okay, that means please remember, if the limit of the sequence is not 0, then it's automatically the series is divergent. And please do always start with the test for divergence, always. Okay, that means this is the, but on the other side, if the limit is 0, we can't say anything. We have to find different test. Okay, that means if the limit is 0, we know nothing. We have to use some test, maybe the integral test. Okay, let's keep moving because we do have nice comparison test, but I can tell you, we almost did the comparison for proving the integral. And from section 7.8, you also did comparison. That means almost nothing, nothing new. The only thing is, using the comparison test, we will always have our question, our series, and we have to find the other series that we will be comparing with. That we do have small extra job to do to find something that is comparable and like easy to state if it's convergent or divergent. Then we can conclude the convergence or divergence for our series. That means, let's see. Let's take something like that. Let's consider the series 1/2 to the n plus 1. And you can probably see it's almost like the geometric one. The only thing is the plus 1 is a little bit weird because we don't have really form like that. We can only see the n in the exponent to say that it's the geometric one. That means this series is definitely the geometric one. Yes, we remember from yesterday. With the first term A, the common ratio 1/2, and if the common ratio is less than 1 or greater than -1, then we can conclude convergence and we can find the sum. Okay, that's we can see this is definitely convergent, the geometric one. You can practice, you can get this information. Now what I can do, we can see they are quite similar. That means I will try to compare. Because having this function, I mean this sequence, this expression, and this one, I can put this relation. Okay, because looking, they are almost the same, except this denominator is greater. If the denominator is greater, the whole fraction is smaller. Okay, that means this is smaller. And now, if we know that this infinite series is convergent, it's actually even equal 1. That means we even lucky we can get the sum. That means everything what is smaller, it will also converge. You can think again, I can repeat what I said for the integral. You can think that convergent is like something limited, like let's say box, the whole box, like the box of items. But it's just the box, it's limited. And everything what is inside, everything what is smaller is also limited by this box. Okay, that means that's how we can compare. If this relation will be the other way, we can't compare. That's implicit. Of course, this is wrong. I'm just trying to show you that if I will find out that this is convergent, something what is bigger, I don't know. Because if you will imagine again, like the shoebox, I have some items and everything what I can squeeze inside is smaller will be convergent. But something that is bigger, I don't know. Maybe it's so huge that maybe it's divergent. That means only this relation. Convergence must be smaller. Okay, and of course we have to always have the positive terms. That means this is less than 1, and that's the comparison. Okay, that means that's how we can compare. If having two series with the positive terms, we can't have negative, because negative, positive, I don't know what is bigger, what is greater. No, that means if the series B sub n is convergent, okay, and we do have this relation, that's what I just showed you. And that the new one, my original series A sub n, the summation of A sub n, it's smaller, then I can conclude that this series is convergent. Of course, something smaller, something that I can fit to my like whatever, like shoebox. Now we can also conclude divergence, but if we have different scenario, we have to have the infinite series B sub n divergent. That means let's say B sub n is divergent. Okay, and I'm trying to figure out my A sub n. But what I have this relation. This is actually greater or equal to. Okay, can you see the difference? If this is divergent, which means like big infinity, or maybe undefined, but we can think, to understand this, we can think that this is infinity, is huge. Everything what is greater than infinity, I think sounds weird, but everything what is greater beyond that, of course, is divergent. Yeah, that means we have to be really careful. If the relation is different way, we can't conclude. And we have to be really careful. But if this is divergent, everything what is greater, it's divergent. If this is convergent, everything what is smaller, it's convergent too. Okay, that's almost everything for the comparison test. That's mean what we have. Okay, that's mean now I do have a list, like how can we compare? Like the first one, I kind of saw that, it's similar to the geometric one. That means I did compare with the geometric one. And we can always try to reduce our rational function just to the form 1 over n to the power of p, and then compare with the p series. Or, yeah, that's actually the same thing. The rational functions, we can kind of simplify and get this. That means this is almost the same. Yeah, that means that's kind of like the hint what we can compare with. Let's do a few problems. Okay, determine whether the given series converges or diverges. Okay, that we can see I do have my formula of the sequence 2n squared plus 4n plus 3. And I would like to compare with something similar. That means what we normally do if we have the rational function, we have to look at the leading terms. That means on the top I have no option, I will keep 5, but in the denominator I will only keep this one. And now, can you tell me the relation, which fraction it's greater, on the left or on the right hand side? Is my left hand side greater or smaller? My right is greater, yes? Thank you. Because we remember one more time, if the denominator is bigger, the whole fraction is smaller. Perfect. That's me now. I have to look closer at this, starting from 1. And of course, I don't have to really copy all the time, but I will from 1 to infinity. A little bit, it's still the same relation. And this one, if I will pull out the constant, which constant doesn't really change anything, I have my formula 1 over n squared. And do you think this one is convergent or divergent? 1 over n squared, we just learned today, is convergent. Yes, thank you, Alicia. Enrin, thank you. Convergent. That means if this is convergent, everything what is smaller converges too. But now, just make sure that you will say convergent by, and I will say comparison test, and let me add the direct comparison test, because I can show you one more thing as always, right? Direct comparison test, because I am directly comparing with this. Oh, actually, direct comparison test with, because what we will do, we will also ask you, when you using the comparison test, you have to show us what you're comparing with, because sometimes doesn't work, yeah? Especially the relation, the inequality. Okay, great, really nice example. Let's see. Oh, okay, oh, that's actually what we did. Oh, I didn't want you to see this, but yes, we will. That's what we have. Do you remember we used the integral test, which was actually quite long. Now what we can do, we can simply use the comparison. That means determine whether the given series is convergent or divergent, ln of n over n. That means what I did, I put ln of n over n, and like, what I can say, I mean, how can I say, theoretically, I can compare my original formula with whatever I want. Of course, must be similar. I have to make this comparison, this relation, but I can compare with anything. That's what I did in this case. I kept n, but ln, right, function ln of n, I did compare with what function n. And we know, with function 1, okay, constant function. And if I draw these functions, ln of n looks like that, and 1 looks like that. This is just the constant. Let's say y and n, or x maybe, because I draw the continuous. And we know that they intersect at e. Okay? That means after e, again this magic number 3 or e, after e, the function ln of n is greater, because constant stays constant. Ln of n is increasing, not fast, but it is. Okay? That means that's the reason that now having ln of n over n, yeah, I shouldn't have this relation, I should ask you, but okay, 1 over n. Now what I have now, since the denominators are the same, we're comparing the numerators. But if the numerator is greater, the whole fraction is greater. And that's the relation. Of course, I have to make a comment that is everything happening after 3. Okay, that means now we found something that is comparable. That means my infinite series, and I can put from 3. It's comparable to 1 over n. And do you remember this one? 1 over n. It's convergent or divergent? We even learned today, or I'm sure Dr. Bank introduced, it's divergent because n is taken to the power of 1. By the p-series test, we can say it's divergent. Do you know the special name for this one, 1 over n? Yes, thank you. It's the harmonic. Harmonic series. It's kind of like from music, the notes. 1, 1/2, 1/3, 1/4, 1/8. Yes, we have, that means probably the name. That means harmonic series is just this one, and it's always divergent. That means perfect. This is divergent. Everything what is greater than infinity is divergent too. That means this is divergent by direct comparison test, and we did compare with this. Okay. Okay, let's see, because what we do have one more form of the comparison test, which will be not direct. Oh yeah, That means that's what I just said. If we have different, like, yes, different relation, if the infinite series is like divergent, something smaller, we don't know. If it's convergent, something bigger, we also don't know. That's, we can't really apply direct comparison test. That's mean what we have. Let's look at this series. It's almost the same like I started this test, but you probably notice is minus. That means I will think that I can also compare, too fast. You can think that I can compare with 1 over 2n because that's the closest similar formula. I can maybe write this 1 over 2 to the n, but now, my writing is too sloppy because my pen, 1 over 2 to the n minus 1. Now we can see, starting from 1 infinity, since I have minus 1, that means denominator is smaller. If the denominator is smaller, the whole fraction is greater. Okay? And now this, we know, is the geometric one and is convergent. Convergent. That means if this infinite series is convergent, like limited, finite number, it's even equal to 1, something what is bigger, I don't know. I can't really compare. That means, please remember, direct comparison test doesn't work. Okay, it's not working. You can't say this. But what we have, like, you know, mathematicians, they will still say, no, this is still good formula to compare. That means what we will do, we will use this formula, but we will use something like limit comparison test. We will compute a limit, and let's see. I will take this new series that I create, which this is the b sub n, this is the new one. This is the original one, a sub n, this the summation of a sub n. And I will take these formulas, a sub n, and divide by b sub n, and I will compute a limit at infinity. That means I will check how the ratio of these functions behaves. And what I'm looking for, I'm only looking for the number greater than 0, for the finite positive number. And we can see finite number greater than 0. If this is greater than 0, then the conclusion are both of them will behave exactly the same. That means if my b sub n, my new series was convergent, the top one will be convergent too. If the b sub n is divergent, this will also diverge. Right? Let's see, that means if this is convergent, using the limit comparison test and satisfying the condition, I can conclude convergence. And then now the inequality doesn't matter. Doesn't matter because I'm not using direct comparison. If this will be eventually divergent, then this is divergent too, if we satisfy the limit. And I can explain you why this is like that. Just do I have, I have this one, but I will not use it. Okay, let's see this. Limit. Let me use function. Let's say ln of x over e to the x. Do you remember, like, limit at infinity and the ratio of two functions? And can you tell me what is the limit of this expression, ln of x over e to the x? Is 0. Okay, that we can see. Is 0, and why is 0? Pete, yes, that's good. Do you remember, like, if we have to look at the growing like rate, which function? Yes, the relative rates of growth. Because we know that the function e to the x grows much faster than ln of x. ln of x, of course, at the moment. Okay, that means if we getting 0, we can see we have ratio of two functions. That means now you realize that the ratio, the limit of the ratio of two functions is giving me lots of information. Because if the limit at infinity is 0, then I will always know that function from the denominator is bigger, faster than the numerator. Okay? Now, what about this limit? Let's say let's say, what I can do. Okay, let's just say this, x squared plus 5 over x minus 1. What about this limit? This limit is infinity, of course. Okay, that's what we can see. This limit is infinity, and if I would like to do the same thing, I can say that function x squared plus 5 is actually growing faster than function x minus 1. That means when we getting infinity, we will always conclude that function from the denominator is faster. Okay, now what I need, I will maybe write on the top. What about this limit? Limit, of course, at infinity, 2x squared minus 1 over 4x squared plus 5. What about this? It's the finite number, right? 1/2, just the ratio of the coefficient, 2 over 4. And can you tell me what do you think, what this 1/2 means? Is one of the function like bigger, greater, or they simply like comparable? Like, they are simply like the same. Can I say they are the same? In terms of of course, of the relative rates of growth. Yes, do you agree with this? Yes, when we getting, yes, I know I'm kind of asking or stating, yes, I'm not. That means if we getting a finite number, yes, finite number, not 0, just the finite number, I can say that this function, it's like, what was the symbol? Something like that. Comparable, or I can say the same from the top and from the bottom, numerator and denominator, they are the same. That means now, I hope we understand this. If we getting a ratio and getting a finite number, then we can conclude that both of the functions behaves the same. And doesn't matter. If this is divergent, this is divergent. If this is convergent, this is convergent. Because this is like a really specific tool. Based on this output, I can conclude both. It depends what B sub n was. Okay, that's the nice thing about the limit. And what we normally do, we only using the limit comparison test. I mean, we using and applying properly if we getting that value C. But what's happened? Sometimes I know that I always find out that it's a little bit confusing for most of the students. But if you understand the bottom of this slide, you may also, you will probably be okay, and I can also accept your answers. But we have to be really careful, because now what's happened? If you, by this ratio, normally, I think even our textbook is telling me that if you're getting 0 or infinity, we're not using the comparison. We can say it doesn't work. But you can still, yes, if we understand the concept, you can still figure out. That means getting 0, yes, you can see 0 means that the function from the denominator is greater. That means if the series was convergent, I can definitely conclude convergence, but only convergence. Yeah, that's the reason that it's a little bit confused, because it's not as general as the top part. But you may still try to use it. If you will get infinity, this means that the function from the numerator was greater, then you can only conclude divergence. That means they are kind of like a special case. You can really pause the video and you can kind of like digest all of the information. Okay, but I can tell you that this is I can use maybe different color for you, maybe blue. This is the general limit comparison test. We're taking a limit of both of them. If we're getting a finite number, correct, both of them are the same. What was Bn? Convergent. Then the A sub n is also convergent. Okay, let's finish our question, this one. Because we did a fraction 1 over, the series, but we couldn't directly compare, okay? That means what I'm saying, my A sub n is my original, and my B sub n is the new one. And I'm trying to apply the limit. comparison, because one more time, direct comparison test doesn't work because of the inequality, the relation. Okay, let's see what we're getting. And I know that this is convergent. I will just write convergent, this one. But I can conclude convergence. Okay, a sub n is 1 over 2 to the n minus 1. Dividing by fraction means multiplying by the reciprocal. That means my limit looks like 2 to the n over 2 to the n minus 1. Do you think you know that limit? It's just the ratio of functions and they are identical, 2 to the n over 2 to the n. The limit, yes, 1, thank you. Thank you. It's 1. That means 1 is the number greater than 0. That means the limit comparison works. Okay? That means I can conclude that this infinite series is convergent because this was convergent. Let me move this. I will move on the side for you. One more time, because we always ask what is a sub n, what is b sub n. B sub n is the new one. I'm trying to organize. The direct comparison test was not working. Okay, but I can conclude this is. I'm sorry, something is. I can conclude convergent by limit comparison test, because the limit, I've got a finite number, positive finite number. That means it's convergent by the limit comparison. And of course, I did compare with this. You still have to provide the formula, but it's not by directly comparing. Okay, please always make sure that we know this. Okay, I think that's everything for today. Maybe we can do, hang on, because I don't know, we can skip. I do have few things. Oh, true and false. Okay, maybe this one. I'm just trying to, maybe we can solve 2 problems just to finalize everything. It's still comparison, but could be direct or could be limit. That means, what do you think? Having a formula ln of n over n cubed, what you will compare with? Ln of n over n cubed. We can keep n cubed for now. We can also change this if you like. As I said, we can compare with everything. And I think I gave you that tip that function ln, I can compare with 1, which this will be always greater. Let's start from 3. And I can compare ln of n with n. This will be greater. That means maybe you can, the blue box will tell you a little bit of the hint. That means ln of n behaves like that, 1 behaves like that, of course, magic number e. And n is simply this. Okay, that we can see n is definitely greater, ln is greater than 1, and 1 of course is. That means what I can try maybe 1. But if I will put 1, what's happened? Oh, actually, okay, 1. Do you think it's correct? Or maybe I can ask you, if I will put 1, having the same denominators, having different numerators, which fraction is greater? On the top? I mean, the left or the right? Left or right? Which fraction? Left is greater, yes? Thank you. Okay, everybody understand this, very good. That means, let's see. Let's start with 3. You know why I'm putting 3. That means, do you think I can compare, or I think I make wrong choice between 1 and n? Because what about my right-hand side? Is this series convergent or divergent? This one is 1 over n cubed, cube is telling me that it's convergent. And do you think I can directly compare? If this is convergent, can I conclude convergence? Not really, if something is bigger, yes? Because again, convergent, you can think something like limited. Yeah? Something which is greater than this, I don't know. That means the direct comparison test is not working. But what I will do, before I use my limit comparison, I would like to try another one. ln of n over n cubed, and I will put n. That means now, can you tell me which fraction is greater? On the left or on the right? On the right now, yes? And I think now, at least I'm getting different relation. I can simplify this and I will have 1 over n squared. Yeah, because n over n cubed is n squared. And this is convergent. Excellent. Convergent. Of course, p is 2 greater than 1. Everything what is smaller also converges. Converges. And I can say by direct comparison test, but please note, we're comparing with this 1 over n squared, not 1 over n cubed. That means this is a nice question to create a multiple choice, because I can ask you, please, I mean, this series is convergent, but did I compare with 1 over n cubed or 1 over n squared? Directly comparing, because I didn't check the limit. And that means you have to say that 1 over n cubed comparison is actually wrong, because this is not letting me to compare. This one works perfect. Okay. Okay, that means I will finish the session, and thank you for staying with me again, really long. I do have few more problems, but I think I can leave it for you. You will be definitely good to compare, okay? And yeah, you can see that the limit, the comparison is quite quick test, nice and quick. Integral is a little bit longer, but both of them are good tests, okay? Thank you, and please put any question on the discussion board. I will be watching the questions, and next week we will have another few tests. Okay, master this one. Thank you.